in this video, I'm going to discuss about some models for first order differential equation. A model means that a models of a problems, okay, that apply first order differential equation. Alright, in this video I'm going to talk about the population growth model. Alright, a population growth model. So where, alright, let's write as population growth model. Alright, population growth model. So as you know that the first order differential equation can use to model some problems. There are many problems that can be modeled by differential equation, but for pre-university level, we're going to talk about first order differential equation, the application of first order differential equation. For example, one of the most simplest is a simple population growth. Alright, I let this to be a P, alright, to represent population. Means that the number of population means the number of peoples, the number of bacteria, so the size of a colony, alright, everything that relate to the number of organism, alright, which is alive, and they are, we name it as simple population growth because we assume that the organism is always increased, okay, it's always increased due to time. Alright, for example, human being, let's say I can define that, I can say that the population growth, the dPdt here, let's say for human, so we can say dPdt is like something like the rate of birth, okay, the rate of birth is always proportional to the current population, right? Means that the bigger the population, the bigger the rate of birth, right? More human, more people giving birth, right? So means that there are more more people, so and more grow, right? So that's why they directly proportional, right? So means that more people, more rate of birth, something like that. Or we said more bacteria, so the rate of growth of the bacteria will be even higher, right? So they are directly proportional. So because they are an increasing model, which this is an increasing rate, so we are said that dPdt can rewrite as a equation that relate by a constant k, right? Can relate by a constant k. So and this become a simple population growth. Alright, simple model for population growth. So how to solve this problem here? Right, we have to find the formula for the current population, right? Means that the population in time of t, the formula of the population at that time. So, and we can solve this by using the concept of separable variable, alright, which will be dp over p, alright, dp over p equals to k dt, right? We can separate it, divide both sides by p, and we integrate both sides, right? As you learn. So now integrate, this is 1 over p, right? 1 over p, integrate 1 over p with respect to the population and integrate k dt. So integrate 1 over p is just like dy 1 over y, so we're getting ln y, right? There are no modulus for this case because the number of people is always positive, right? So the number of organism. So now for this case here, this is a constant. Integrate 1, you have t plus a constant c. So this is the solution, the general solution of this model. But as we want, this one will be p. And now I want to write p in terms of t, right? Because I want the formula for population. So I have to rewrite this as I know that this is a log e, right? Kt plus c. So I can bring the e go the other side. I make e kt plus c, right? E kt plus c. And c is a constant, alright? You have to know that c and k is a constant, alright? They are constant. So means that I can further rewrite this into kt multiply with e to the power of c. And of course, if c is a constant, e is also a constant, means that ec is also a constant. I can rewrite this just, usually we were using a, alright? Just rewrite this to be a, is another constant. So lastly, we know that the population growth, the formula will be a e k t. This is the most simple population growth, where it's not affected by other factors. For example, like war, alright, using maybe immune system for the bacteria, right? We have immune system to fight the bacteria. Means no, we are assume this model that the population is always grow. Bacteria is keep growing. The human is keep growing, alright? Without any other factor. So this is called simple population growth. So as our objective here in this concept here is we have to identify the A and the K for the types of population that you being researched, right? You want to find out what is the constant that can relate to that model. Alright, so we have different type of cases, so we have different type of A and K. So let's look at the examples. Alright, in these examples, so you can get the notes from my Telegram groups, or you can get it from my WhatsApp on my YouTube channel. So you can get the question from there by clicking at the link below the YouTube channel or my Telegram. Alright, so let's look at this question here. The question is telling that the population of a certain bacteria, alright, the population of the certain bacteria grows at a rate proportional to the total population of the bacteria at time. If the population of the bacteria started with 1,000 bacteria and after 2 hours, it is estimated that there are now 8,000 bacteria. They are actually telling you that the model, right, is a population that relate to bacteria grow. Alright, let's look at this question. So it said that the population of the certain bacteria grow at a rate. Certain bacteria, okay, you can using P, population of the certain bacteria grow. This is the rate, right? Rate of change. So means that rate of growth of the bacteria proportional to the total population of bacteria at that time. Okay, proportional to the total population of bacteria at that time, right? Means that at that particular time, they are directly proportional. Means that the population, the more the bacteria, the more the rate of growth. So they have defined for you, if the population of the bacteria started with 1,000 bacteria, means that started means that during initially when we count start from t equals 0, the time 0, so the population is considered to be 1,000 bacteria. Alright, this is how we define the variable. And after 2 hours, the population of the bacteria is now 8,000, right? It's grow quite fast, right? It's very fast because in just 2 hours it become 8,000, right? So, and they give you this initial conditions, and you have this model. So you have to solve this model by using the population growth model, which is dp dt equals to kp, where you already know how to solving this by using separable variable. So as you solve, you get dp over p, which is equals to k dt, right? Then you integrate both sides. Then finally you have ln p equate to equals to k t plus c, which I derive again for you. So p is exponent kt multiply with ec. Do you know why? Because exponent e to the power of kt plus c, where the plus c is represent multiply e to the power of c. And I used to write p equals to a EKT. This is the one that I derived just now. So I derive it again one more time. So we are using this model. All right. We have to show why we are getting this. Right. So we have to define the model. So after we get the model in the form of differential equation, we solve that differential equation and we get the formula. But this formula can't be used yet because we have A, we have K. So we have to find the value of A and K. So of course, these two information here is for us to find the value of A and K. So as we know that when T0, population is 1000. So it means we can improve this formula by writing when the P is 1000, right? P is 1000. So the E, the KT, so K multiplied with 0. So we have E to the power of 0, which is A, right? So we have A equals to 1000. So it means that P equals to 1000 exponential KT, right? Now we have know the value of A, right? But we have to improve the formula until we get the value of A and K. So how to find the value of K? So we have second information, right? Which is given. So we know it's 8000, right? 8000, then which is equals to 1000 when the time T is 2. So 2K. Very simple, right? So as you divide both sides by 1000, you have 8 equate to exponent 2 to the power E to the power of 2K. So there's we can find the value of K. So by putting ln both sides, so we have ln 8 and we can bring down the 2. So 2K ln E is 1, right? So ln 8 and K will be 1 over 2 ln 8. All right, 1 over 2 ln 8. Or we can rewrite this with 1 over 2 means that square root of 8. You can change also into decimal. You can change this into decimal, but it's less accurate, right? So of course I prefer using the exact value of K. So I have K equals to ln square of 8. So now finally I have my complete formula for this population, for this bacteria. Different bacteria have different K, right? Have different K. Why? K is the rate, the constant rate. So the rate of growth of the bacteria, right? Different bacteria. So population is equals to A, which is 1000, right? 1000. Exponent ln square root of 8t. This is the formula for that, the formula for population of that particular bacteria. That's why we said this is a particular solution just for that bacteria. So then we have answered the question A, right? We have get the number of bacteria at time t. So of course we can answer this question as after we have the formula, we can using this formula to solve anything about the population of this bacteria. Okay, the question, find the number of bacteria after 1 hour, right? After 1 hour means we know that after 1 hour we were using this formula, we were getting the number of bacteria after 1 hour, which is 1000 exponent ln square of 8. Just substitute the t by 1, then we can get the number of bacteria, right? So try to key in your calculator and get that number. All right, which is around, okay, it's around 2828 bacteria. All right, so after 2 hours it will become 8000, right? So it's an exponential model, which is not a linear model. All right, if you see that 1000 become 2000, suddenly become 8000 in 2 hours. So if you find after 4 hours, the number of bacteria become more, right? Bigger, okay? In a shorter time, the number of bacteria grow very fast. All right. So, and now we go for, they also can be used to find the time taken. Okay, we want to see the time taken for the bacteria to become 15,000. All right, the time of bacteria for the bacteria to become 15,000. All right, so we can doing this way. So it means that we have the formula here to be P equals to 1000 exponential ln square root of 8t. So now the time when the population of the bacteria become 15,000, right? A lot more. So 15,000. So it's 15,000 for the population. So we want to investigate what happened for this model here. So as we see, we just solve the logarithmic equation here and the exponential equation here. So we have 15 equals to exponential ln square root of 8t. So we want to bring this down, we have to put ln both sides. Ln 15 equals to ln e ln square root of 8t. Right? Alright? Okay. So we put ln, and we have ln 15 to be equal to ln square root of 8 multiply with t, right? As we can bring this forward, ln e will be 1, right? 1. So we can say the time taken to become 15,000, the population will be taking the ln 15 divided by ln square root of 8, which give you 2.6 hours, around 2.6 hours. Alright, means initially you have 1,000, right? After 1 hour we have 2,800 something, right? And 2 hours we have 8,000. After that, just 2.6 hours we already reach 15,000, right? So this is a growth model. That's why we say it's to be an exponential model. Can you see? Because they grow very fast. Alright, it's an exponential growth model. So if you see that, it's growth very fast for the bacteria. Alright, means that the bigger the bacteria, the size of the bacteria, the bigger the rate of growth. Alright, so that's all for this video. Hope you understand how to solve the problem involving application of first order differential equation.